Okay? So if we simplify that down a little bit, exchange or transfer of an atom other than hydrogen. Okay? That could mean a full functional group switch, but it doesn't have to be. Okay? What is an elimination?
Breaking a bond.
Breaking a bond.
And gaining a double or triple bond.
Okay? So elimination, we have to eliminate something from the structure. We have to break it away. Okay? In that process, it's actually going to be the breaking of 2 sigma bonds. Okay? Resulting in the formation of 1 pi bond. Okay? That's a big thing to distinguish. Because when we think about eliminations and we look at our elimination reactions, particularly if you think about an alkyl halide, if I was to take this structure and turn it into this, what does it look like I did?
It looks like you only got rid of chlorine.
It looks like the chloride was broken off. We could get through with balancing. Balancing, for the record, is something I'm horrible at. Most organic chemists are really bad at it. Okay? If you need me to balance, just shout it out that you want me to balance. That would match the definition that you guys just put together. Formation of a pi bond and broke a bond. My definition says we lost 2 sigma bonds. What's the other sigma bond? Oh, yeah. What do you mean, oh, yeah? A hydrogen. There's obviously a hydrogen there. There's obviously a hydrogen there when we include it. Okay? How easy is it to lose that hydrogen? Very, very easy. This is why it's important to try and remember those key pieces on what's breaking, because it can help you go through a structure and be like, I have to get rid of that piece also. It can layer that information in. If you don't have the proper definition, it's very easy to ignore that aspect, and you might miss out on key important reagents. Make sense? Okay. Because you guys have been doing awesome in the back there. Knock it off. Addition. What's the definition of addition?
Removal of 1 pi bond, resulting in formation of 2 sigma bonds.
Okay. Removal of a pi bond, formation of 2 sigma bonds. Awesome definition. I think that's exactly what I wrote. Let's see. Cool. Can someone give me a different answer? Yes. Yes, you can. Didn't quite work the way I wanted it to there. What is an addition reaction? It's the opposite of an elimination. Okay? So again, we'd still have to remember, that elimination had 2 sigma bonds with that tricky hydrogen. When I do the addition, I'm going to have to remember that same little piece. Okay? And radicals, you can see my opinion of radicals right here. There are 2 main branches in radical reactions. You can get substitution reactions and you can get addition reactions. So you'll get radical substitution, radical addition. Okay? Fun and exciting. At some point, we'll talk about them again just to kind of review that content, but that's going to be about it. Okay? So if you're awesome at radicals, I'm sorry. Anybody feel like they're awesome at radical reactions? Cool. You just remember the dot? That's fantastic. I'm right there with you on that one. Okay. So the next part is also knowing something about what they look like. Because when you look at a test, it's not going to give you all this text of what these things are. It's going to give you the structures. Okay? So this slide I find really important because it summarizes the text of what's happening in those and gives you structure patterns within them as well. You'll notice I am dropping in some other kind of weird terms. Like solvent, really foreign one, right? That would represent some of you smirked, so those of you that smirked would represent the
liquid, whatever it's being dissolved in.
Also known as the
Solution. Solvent.
Damn, good. You actually came up with a different word. Yeah, solvent. That's all I was going with. The solvent represents the solvent. It's what it's all in. Yeah. Okay. Tends to play a more minor role, which is also why I picked green as a color, because the green tends to fade out on our projectors and become kind of illegible. Okay. So not as big of a deal. What about NUC? Nucleophile. What does the nucleophile do? Donates electrons. To donate electrons, what might we expect to see on the nucleophile?
Electrons.
Electrons, right? There you go. 2 dots. Okay. You'll notice in front of it we see M/H. Metal or hydrogen. Okay. How does that change things? If it's a hydrogen, well, here, you answer first.
So metals and hydrogens, what they have in common is they throw away the electrons.
True. They would both throw away the electrons. How would that affect the nucleophile?
I got lost.
You're right on.
The hydrogen makes it also an acid.
The hydrogen could make it an acid. Okay. But I asked about the nucleophile. You're like, Mike, that question is way too hard. So one of the things that you could, if you hear me ask a question where you're like, I have no idea what he's talking about, that's way too much. Throw in an example. Okay, let's pick the easy one because hydrogen's right there. Let's do HOH, right? Everybody agree? There's the nucleophile. We could even draw on, in this case, 2 lone pairs. Yeah? So, well, that's one of them. Give me a metal.
Lithium.
Sodium, something like that.
I'm going to stick with sodium because I think most people will pick up on sodium a little bit better. What is the difference between those two? That purple one is now strong. The red one is weak. How do we know that?
Does it have to do with the size of the atoms?
In this case, unfortunately not. That's not the primary driver here. What is the difference between sodium and hydrogen? Electronegativity. Okay. The metal electronegativity is so much lower that what happens to the electrons in that bond?
They break easier?
They break easier. They break easier which direction?
Break to oxygen.
To the oxygen, which means the oxygen, the purple oxygen, is more likely to be negatively charged. A negatively charged species happens to be a stronger nucleophile than a neutral one. Okay? All of that information is embedded in those notations. This is why OChem is really neat. You can embed a crap load of information, so much so that you're like, just stop putting more information in there. Okay? And then we still have 16 more weeks. Okay? LG? Leaving group. Base. What's the difference between a base and a nucleophile? Yes, I do that too.
They're pretty much the same thing.
Pretty much the same thing. Define a base.
All nucleophiles are bases, but not all bases are
Okay.
nucleophiles.
This is going to be a big switch, actually, between... Dang. We'll pretend. I think it's coming up here, but there might be somebody at the door. Who is that? Yep. Sorry, I must have seen somebody else. When we look at our difference, for those of you that weren't paying attention, we just skipped some stuff. Protons, acids are proton donors. Electrophiles, electron acceptors, right? Who cares? We didn't ask about it. We asked about base and nucleophiles. A base is a proton acceptor, right? What is a nucleophile? An electron donor. To accept a proton, what must the base have?
Electrons to donate to the proton.
So doesn't that mean the base is donating electrons? Yeah.
So this is like the acid, the Bronson-Lowry kind of
Yes. This is exactly what it gets into. Okay? When we look at these definitions, these are effectively the same thing within each of these boxes. Okay? And it took someone looking at all these reactions to go through and say they are the same thing. Okay? And it all centers on how the electrons move, which is why we get the definition of Lewis acids are defined as electron acceptors. Lewis bases are defined as electron donors. But what does a Bronsted base do? It accepts protons. But didn't it have to donate electrons? Yeah. So when I say base, what am I referencing? What is that base doing?
Accepting a proton by donating electrons.
Is it accepting a proton? Or is it donating electrons to something else? It could do both. And this becomes the differentiation between these definitions. Okay? Lewis covers everything. And because it covers everything, it's pretty much a useless definition. Right? So when I talk about acids and bases, I am not referencing the Lewis definition because it covers too much. When I talk about acids and bases, I'm talking about Bronsted-Lowry. Well, what does Bronsted and Lowry reference?
And what's the third one?
Bronsted-Lowry only looks at the protons.
And then there's the third one?
Well, what if something donates electrons, but it's not donating electrons to hydrogen?
Then it's an Arrhenius.
All right, and I don't even want to open that one in. Arrhenius is just bad. Let's just ignore that one. Okay? I still want to be able to reference this chemistry. If I go through and say, well, it's donating electrons and call it a Lewis base, now what becomes the problem? I'm now referencing things as Lewis bases and Bronsted-Lowry bases. Do you hear, comprehend, and hold every single word that comes out of my mouth?
Yes.
Okay? Which means if I go through a reaction and refer to a Lewis base, you may be like frantically writing base, but then forgot to write the Lewis. You go back and look at it, and you're like, well, he wrote base, so it must be Bronsted-Lowry. So you write Bronsted-Lowry next to it, and now you'd be wrong because it was supposed to be Lewis. So I don't use the Lewis term because it's way too broad. The extra definition that we bring in is this nucleophile and electrophile. Those match the Lewis definition with one caveat. Electrophiles and nucleophiles will not donate or share electrons with hydrogen ion. Because if it deals with hydrogen ion, it's now going to be a Bronsted-Lowry. It's already getting confused. A Bronsted-Lowry acid and base. Okay? So that's why when we look at this slide, it boils down to just this. Acids and bases, proton donor, proton acceptor, electrophile, nucleophile. Those are the four reaction types that we're going to deal with. How do we differentiate bases from nucleophiles? They both donated electrons. But what does the base donate electrons to? Hydrogen. So how do you know you're dealing with a hydrogen?
It's a base.
Base or a nucleophile?
Base.
I apologize.
Well, it's what they call that thing?
Base or a nucleophile?
Nucleophile.
Damn, you were wrong.
Well, you could draw it a different way, and I'll be right.
Exactly right. How do we know what hydroxide is acting as?
In context.
We have to look at the larger context. You have to look at the rest of the structure and say it is reacting with an acid, which means hydroxide is acting as a base. You have to have that broader context to differentiate bases and nucleophiles. You have to. Okay, with that, I've already talked too much. I'll answer your question, but